Hi all, in this video I cover one of the important mathematical tools used in many engineering applications called eigenvalues and eigenvectors. To explain the concept, I am assuming A is a square matrix of size n by n and V is a non-zero vector and lambda is a scalar. Then if there exists a relation between these three as AV is equal to lambda into V, then we can say lambda as eigenvalue of A and V is eigenvector of A corresponding to lambda. The eigenvector is also called as characteristic vector of A. Now I am going to give you three different computations. First one is given the matrix A and eigenvector V, we need to find out the corresponding lambda. And the second one is given A and the eigenvalue lambda, we need to find out the corresponding eigenvector V. And the third type of computation is given only the matrix A, we need to find out all possible eigenvalues and the corresponding eigenvectors for the given matrix A. Now the first example is the matrix A is 2 by 2 matrix which is having the first row 5 4 and second row 1 2, and then we need to find out the eigenvalue lambda. In the first case at eigenvector V is equal to 4 1, in the second case the eigenvector V is equal to 1 1. Now consider the first case where eigenvector V is equal to 4 1. We already know that the relation is AV is equal to lambda V. By substituting the values of A and vector V, we will get the lambda is equal to 6. So that means the eigenvector V is equal to 4 1 of the matrix A corresponding to the lambda value 6. In the next case I am considering the eigenvector V is equal to 1 1. Again I am considering the same relation AV is equal to lambda V. After substituting the values of A and vector V 1 minus 1, we will get 1 minus 1 is equal to lambda minus lambda. Then we will get the lambda is equal to 1 from this very clearly. That means V11 is the eigenvector of the matrix A corresponding to the eigenvalue lambda is equal to 1. Next example. Here we need to find out the eigenvector V of a square matrix A corresponding to the eigenvalue 4. For that we have the relationship AV is equal to lambda V. After substituting the values of A and lambda, we will get 2x plus 2y is equal to 4x minus 4x plus 8y is equal to 4y. After solving these two equations for x and y, we will get x is equal to 1 and y is equal to 1. Then we got the eigenvector V is equal to 1 1 for the corresponding lambda value 4. So next thing is finding the eigenvectors of a matrix A, which is a square matrix of size n by n. Here we have only the information of the square matrix. We need to find out all possible eigenvalues and the corresponding eigenvectors now. Before going with example, let me cover how to find out this theoretically. So we have the definition AV is equal to lambda V. Then we know that if you multiply any matrix with identity matrix, there won't be any change for that matrix. Then I am going to write V as IV, where I is the identity matrix. Then after rearranging this, we got AV minus lambda IV is equal to 0. So by taking V as common, we will get A minus lambda I into V is equal to 0. We already know that V is a non-zero vector. Then this equation will have only one solution, that is determinant of A minus lambda I is equal to 0. This equation is called as characteristic equation. The degree of this equation is n. So for this equation we can find total n number of roots. These roots are nothing but the eigenvalues of the matrix A. Then we need to find out the eigenvector corresponding to each of the n eigenvalues. So that gives us n eigenvectors of the matrix A of size n by n. Then summary of finding eigenvectors of the given matrix A. The first step is we need to write the characteristic equation of the given matrix A, and then we need to find out total n number of roots for the given characteristic equation, and then at each value of lambda we need to find out the corresponding eigenvector by using this formula. So finally, if the matrix is of size n by n, we will get n number of eigenvectors corresponding to eigenvalues. To explain this, I am considering the matrix A as 5, 4, 1, 2. Then the first step is we need to write the characteristic equation of this. We know that the characteristic equation is determinant of A minus lambda is equal to 0. After substituting the matrix A and identity matrix, we will get this. Then the determinant of this 2 by 2 matrix is AD minus BC is equal to 0. Then finally we will get the characteristic equation from this as lambda square minus 7 lambda plus 6 is equal to 0. Then the step 2 is we need to find out the roots of this characteristic equation. Those roots are nothing but our eigenvalues. So we can write this equation as lambda minus 6 into lambda minus 1 is equal to 0, where the roots are 6 and 1. Then those roots are now our eigenvalues. As a third step, we need to find out the eigenvectors. One is at lambda is equal to 6, another one is at lambda is equal to 1. First, we will find out the eigenvector corresponding to the eigenvalue 6. We have the relationship AV is equal to lambda V. Then I am substituting the values of A and lambda there. After solving these equations, we get x is equal to 1 and y is equal to 0.25. Then our eigenvector V1 is 1, 0.25 corresponding to eigenvalue 6. Then we need to find out the eigenvector corresponding to the eigenvalue 1. We are following the same procedure again. Then we got the eigenvector minus 1, 1 corresponding to eigenvalue 1. Now we look at how you can find eigenvalues and eigenvectors of a given matrix by using Numpy module of the Python. Now I am importing Numpy with alias np. Now I am creating Numpy array A, that is 5, 4, 1, 2. The linear algebra submodule of the Numpy is having a method Eig to compute the eigenvalues as well as eigenvectors of given matrix. If I unpack those values, I will get eigenvalues into the first variable and eigenvectors into the second variable. And then I am using print statements to display both. Now I am running this cell. Then I got 6 and 1 as eigenvalues and a matrix I got which is having all the eigenvectors. Here we have two eigenvectors. The first column gives us the first eigenvector which is having 0.97 and 0.24. You know that the Numpy uses the floating point values by default. 0.97 is approximately equal to 1 and 0.24 is approximately equal to 0.25. So that is the first column we have, and which is the eigenvector corresponding to eigenvalue 6. And coming to the second column, so which is having minus 0.7 and plus 0.7 as a vector. So actually we need to get minus 1 and 1 as far as theory is concerned, but even you get minus 0.7 and 0.7, the equations are solved without having any problem. So minus 0.7 and 0.7 is a vector associated with eigenvalue 1. Now I am going to display these two print statements. The first one is giving the eigenvector associated with the first eigenvalue, and the second print statement displays the eigenvector corresponding to the second eigenvalue. If I run this, then I got these two statements. Now I am going to show you how to find out the eigenvectors and eigenvalues in MATLAB. Now A is our matrix which is having the first row 5, 4 and the second row 1, 2. If I press enter, we will get A as 2 by 2 matrix. So the MATLAB is having Eig as a function to compute the eigenvectors as well as eigenvalues of the given matrix A. If I press enter, then we will get the eigenvectors as a matrix into the first variable and eigenvalues as a matrix into the second variable. See, if you observe the eigenvalues, we will get as a main diagonal in the second variable. From this you can say the first column of this matrix 0.701 and 0.2425 is the eigenvector associated with the first eigenvalue 6, and the second column of this matrix minus 0.7 and plus 0.7 is the eigenvector associated with the eigenvalue 1. This is the end of this topic, and I will meet you with a new topic in the next video.